Section 2.1, Describing Graphs of Functions. What we want to be able to do is we want to be able to use the derivative now as a tool to assist us in describing or recognizing what functions look like in general. And if you recall from a previous pre-cal course that you may have taken, we could find an awful lot about the functions and what their graphs looked like just by a handful of rules. One thing that we weren't able to do was guarantee where maximums and minimums actually occurred, and I claim that now, with the derivative, that will be added to our toolbox. But let's start by talking about increasing and decreasing on a graph of a function of f of x. Well, a function is increasing if the graph continuously rises from left to right. That is, the function is increasing. Now, when this happens, realize that the graph has a positive slope. And when I say positive slope, I mean instantaneous positive slope. So really what that means is that the first derivative is going to be positive for all the values anywhere the graph is increasing or rising from left to right. If the graph continuously falls from left to right, then the function is decreasing. And when this happens, the graph has an instantaneous negative slope for all the values where it's falling. And so the derivative, or the first derivative, will have to be negative for all the values in there. Now, when looking at a graph, we're going to say that a point on the graph in which function changes between an increasing to decreasing, or vice versa, is called an extrema. Specifically, if the graph changes from increasing to decreasing, we're going to call that a relative maximum. And if the graph changes from decreasing to increasing, we're going to call that a relative minimum. Now, I need to make a statement real quick, and that is there's this thing called a relative maximum and a relative minimum, and there's also what's called the maximum and the minimum. And so the maximum, or sometimes called absolute maximum, is the highest point on the graph overall. So if you can look at the entire graph and there is one value that is taller than all others, or equal to, then we would call that an absolute maximum, or sometimes just a maximum. Whereas, if we say that a function has a minimum, that means that it is the smallest value, or the lowest value on the entire graph. And so, realize that these maximums and minimums can occur at the relative maximums and relative minimums, or, if you have a graph that ends, it could occur at the endpoints. So if ever you're asked for maximums and minimums, not relative, then you need to check you have to check relative extrema and the endpoints to confirm where you have absolute maximums or minimums. So now we want to look at the function. We want to identify where the function is increasing or decreasing, and then we're going to label any relative maxes or mins. Now, when labeling or identifying where a function is increasing or decreasing, it is okay for us to write this in interval notation. And so I'm going to write the interval notation in addition to marking it. And so when we look at this function and we see where it's decreasing, how about I trace decreasing? Well, decreasing, if I'm assuming this graph continues forever, it's decreasing from here to here. And then it's also decreasing from here to here. Now we can also mention that this function is increasing and decreasing when dealing with inequalities or interval notation. And so notice that this function is decreasing when x is less than -2. That's that far left part. Also notice that it's decreasing between x being 2 and x being 6. And so when x is between 2 and 6, it is also decreasing. Similarly, we could see where this function is increasing. So as it rises from left to right, notice that that section is increasing, and so is this section. Now I'm assuming that this goes on forever because that's all they've given to us, and therefore if I wanted to write the inequalities for the increasing parts, I would write them in terms of the x, and that would be from -2 up to 2, and then from 6 and to the right, so anytime x is greater than +6. And so those are the intervals or the inequalities. But now that we know where we change from increasing to decreasing, at this point we can find the extrema. And so specifically, if I'm going to label any relative maxes or mins, well, that's anywhere I change from increasing to decreasing or from decreasing to increasing. And so I have relative extrema here, here, and here. So specifically, I have a relative minimum, where specifically that minimum, if anyone asks you, is the y value 1, but it occurs at the x value equal to -2. Up here, I have a relative maximum, and that relative maximum is the y value 3, but it specifically occurs at the x value equal to 2. And so if anyone asks you for the maximum, you could give the y value, but they may also ask for the ordered pair, so realize that just understanding the nomenclature here is what's important. Then down here, I have a relative minimum again, and the relative minimum is 1, and it occurs at the x value equal to 6. Now we want to look at these images and we want to think about which one of these has a positive first derivative for all of the x values. Now, if we make the claim that the functions we're about to choose have positive derivatives for all x values, that means that the entire thing has to be increasing as we move from left to right. And so when I look at that very first one here, notice that every bit that I'm seeing is increasing as I move from left to right. Therefore, I would say that this is actually one of those functions. This one does have a first derivative greater than 0 or positive for all x's. Well, then let's look at this next one. Well, this next one, parabola, if you recognize that, is decreasing from here to here and increasing after that. So that's not one of our situations. This does not have a positive first derivative for all of our x's. It has a negative derivative to the left of 0 and a positive derivative to the right of 0. So that's not our situation we're looking for. Then our next one, let's trace it from left to right. Notice that this thing is decreasing or falls as we move left to right. Therefore, it has a negative derivative for all x's. That's not the one we're looking for. Then I have this graph here. This one, as I read left to right, is increasing, and so I claim this one does have a positive derivative for all x's. That is, f prime of x will be positive for all x's. Now we're going to talk about this thing called concavity. Okay? And so there's a thing called concave up, and there's a thing called concave down. And real quick, just to mention what these things are, it just means that the curvature of the graph either is a smiley face or a frowny face. Okay? So when we mean concave up or concave down, that quick sketch is what we mean. It's kind of bowl-shaped or it's hat-shaped. So, if the slope of the graph increases as we move from left to right through a point, and that point's going to be AF of A, then f of x is said to be concave up. Specifically, that says that f prime of x is increasing, so its derivative, f double prime of x, is positive. And so now we're throwing in some more meaning. The idea here is that if you're talking about the change of your first derivative, if it's positive, then we have a concave up function. And what do those look like? Those look bowl-shaped of some variety. They have curvature that kind of scoops up. On the other hand, if the slope of the graph decreases as we move from left to right through a point, and that point's a f of a, then f of x is said to be concave down, or we could say that the first derivative, f prime of x, is decreasing, and so its derivative, f double prime of x, is negative. Then we're going to say that a point on the graph in which the function changes between concave up and concave down, or vice versa, is called an inflection point. So now let's look at this and let's identify where the following function is concave up, where it's concave down, and any inflection points. Now I am going to label these in terms of inequalities, but you could convert those inequalities to interval notation if you so desired. So let's do concave down first. Well, I see that the upside down bowl shape is between these segments, and so this is concave down, or specifically you could say that's where the x value, or that's for the x, that is concave down for the x values between 0 and 4, and so I'm going to say that between 0 and 4. So if you were trying to label the inequality or write the inequality for where this function is concave down, it's concave down between 0 and 4. Well then, if we want to talk about concave up, where is it bowl-shaped? Where could you hold water? And so I'm going to say that all of this, as far as I know, because I have to assume the trends continue, is concave up, and so is all of this. And so these are our concave up sections. And in terms of the x values, well, on this left side here, the x value being 0 there, so this is where x is less than 0, it's going to be concave up. And here, when x is greater than that x value there, 4, it's also going to be concave up. Now, the truth is once you sketch or realize concave up and concave down locations, it's very easy to locate our inflection points. Specifically, that's anywhere we change concavity. And so I claim that we have two inflection points at 0, 2 and at 4, 2, and those are the inflection points 0, 2, and 4, 2. Now something to mention is that inflection points will have a second derivative being 0. Okay? And so that's a useful piece of information, is because when we start talking about first derivative, second derivative situations, inflection points will have a second derivative being equal to 0. But be careful, because not everywhere the second derivative of 0 is an inflection point. Now let's consider the points on the graph a, b, and c. I want to look at each of these points and I want to say whether the function value at that a is positive, negative, or 0. I want to say whether that first derivative at that point is positive, negative, or 0, and whether the second derivative at that point is positive, negative, or 0. And so I'm going to be a little abusive in my notation, and I'm going to say f of a here, but what I really mean is take the x value for that point a, plug it in, and then that's what we're doing. But if I take the x value for the a here and I ask what is the value of that function, well, it's obviously 5, therefore it's positive. And so since we're really just answering positive, negative, or 0, it's positive, we're good. Then how about f prime of a? Well, remember that's the slope of the tangent line, so if you were to sketch in a tangent line, and we're really just going with our best visible information, that appears to have a first derivative or a tangent line of 0 because it's flat. Great. Then I want to talk about the second derivative. And this is new to us, but second derivative is just an indication of concavity. And so if the function is changing in slope in a positive or negative way, that's actually really what's happening when we talk about the second derivative. And so I'm going to trace this. I'm going to state what's happening to the slope of the tangent line. Well, so here, notice that the tangent line looks like this, more or less. Here it looks like this, and here it looks like this. And so let's refer to what's really happening as we move along the function. Well, that slope, if you were to actually calculate them, that is a decreasing, 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 decreasing slope. And because the slope itself is decreasing as I pass through that value a, I know that the second derivative will also be negative. But if nothing else, you can say, oh look, it's cap-shaped, it's an upside-down bowl, a is in that upside-down bowl, it's going to have a concave down, which means that the second derivative will be negative. Let's do the same thing for b. Well, at the x value for b, what is the function value? Well, the function value here is on the x-axis, so that means that the function value is 0. Well then, let's ask ourselves about the second derivative at the function, at the value b, at the x value for b. But slope of the tangent line here looks like that. That's a negative tangent line, and so, since that's the case, I can say that the first derivative is negative at b. Then we want to talk about the concavity, or what's actually happening with the slope as we move through the point b. And so f prime of b, notice a couple things. First off, if this section here is concave up, this section here is concave down, I claim that via my observation, b should be an inflection point. That is, where concavity changed. Now, to also notice that the slope of the tangent line there appears to be negative, and it appears that it's not changing much on the other side when we talk about the slope of the tangent line, and so the slope isn't really changing at b, and therefore I claim that it's actually going to be 0 for all of those reasons. But I think the easiest one is to notice that it's an inflection point changing from the cup shape, the cap shape, to the bowl shape, so point of inflection has a 0 second derivative. Let's calculate f of c. Remember, I'm thinking of the x value for c, but that's below the x-axis, so that's going to be negative. Negative. Then the first derivative at c, well, slope of the tangent line, that's positive, and so that's positive second derivative. And then we have concave up through c, or if you're looking at the change of the slope of the tangent line, it appears to be an increasing change of slope. Either way, the second derivative here is positive. Now that we need to draw the graph using this information that we've learned about the first and second derivative, just as a reminder, remember that f prime of a being greater than 0 means that we have an increasing function. F prime of a being less than 0 means that we have a decreasing function. And then f double prime of a being positive, being greater than 0, that is a situation where we are concave up. And then f double prime of a being less than 0 or negative means that we have a concave down function. Now to consider how these things interact together. And so specifically, if I have f prime of a being greater than 0, that is, we have an increasing function. Well, if the second derivative is positive, then we are concave up and we're increasing. And so what does a concave up increasing function look like? Well, it looks something like this. Concave up, but increasing. Well then, let's say we have an increasing function, that is concave down. What does an increasing function that's concave down mean? Well, remember, as we move left to right, we must be moving up, but we also have this idea that we have to have a concave down function. And so the concavity being down, that is cap-shaped, while also increasing. So that could look like this. And there we have a concave down increasing function. Well, now let's say that our first derivative is decreasing, and we have a concave up function. So a decreasing function that is concave up. Notice that as we move left to right, we must go down. As we move left to right, we must fall. And so we fall in this direction, but we have concave up. Well, in the situation where we have a decreasing function but we're concave down, decreasing function that's concave down could look something like this. Well, now we're going to use these pieces of information to actually sketch a small portion of graph. So first, notice that we have f of 18 is equal to 4. Well, what is this actually telling us? This is going to tell us the location. Specifically, we have the ordered pair 18, 4. So we know that 18, 4 is going to be a point on the graph. Well then, if f prime of 18 is 4, what does that really tell us? That tells us that the slope of the tangent line at 18 is a slope of 4. Well, we can also state that is an increasing function, or it's increasing at the point 18. Then f double prime of 18 is equal to negative 2, but what does that tell us? That specifically that tells us that we have a concave down function at the location where x is 18. Thus, I can sketch this function, but realize the sketch is just that. It's going to be a sketch where we're limited. Specifically, we can only get really close to that point 18 and know that we're actually accurate. And so since I know that 18,4 is a value on the graph, well, 18,4, we know that that point must show up on the graph. Then what else did we say? We said that the slope of the tangent line at that point is positive 4. And so we know that it's increasing and it's concave down. And so concave down increasing through that part of the function. We can't sketch much, but I claim that that small section there, I've just added the arrows on the end, that small section is close enough. We can't really sketch an awful lot more because we don't know much more about the function. We only know at that specific point. But let's consider that if we're given more information, then we could probably get a better sketch. So we have this first thing, f of 2 is equal to 3, so we get the location 2, 3. Then notice that it tells us that f prime of x is greater than 0 when x is less than 2. Specifically, this is increasing when x is less than 2. Here we get that f prime of 2 is equal to 0, but f prime of 2 being equal to 0 means that we have a tangent line of 0, which means that we're really either going to have, which really means we're going to have a flat spot on our graph there, right? So this is a horizontal tangent line. Then I've got f prime of x being negative anytime x is greater than 2, so that's going to be decreasing when x is greater than 2. And then lastly, we're told that f double prime of x, that is the second derivative, is negative, less than 0, for all x of this function. That is the entire function. Since it does say all x, the entire function is concave down. So then we can sketch this, give myself an xy coordinate plane. I recognize that I have the ordered pair 2, 3, not quite to scale. And then to sketch this, of course, I get the ordered pair 2, 3. But to the left of that x value 2, we know that it's increasing, so it's going to be increasing on the left side. It's going to be decreasing to the right of that point 2. It's got a flat spot at 2, and the entire function is concave down. And honestly, I have an image of, well, increasing with concave down, decreasing with concave down, and then this flat spot up here, it looks like this parabola shape.